Good morning, everybody. All right, so continuing with solving exponentials. If I look at number 3, we first identify it as an exponential equation because I see that we have variables up in the exponent. So I want to try to rewrite these as the same base. So if I look at 1/2, the only way I can rewrite that as a smaller base is 2 to the negative 1. Now 16 I could write as 4 squared. But since I can't write those as the same base, 4 squared isn't going to work for us. So instead, we would want to use 2 to the 4th. Now, I recommend that you work through this one yourself, so pause the video here. And for your final answer, you should have gotten x equals negative 1/13. So if you have questions on that one, feel free to send me an email and I can walk through that one step by step. Same goes for number 4. This one I do recommend that you try on your own. And you should have gotten x equals 0. So again, be careful with your fractions. Remember, you're going to focus in on your denominator first, which would be 9. See if you can rewrite that as a smaller base, and make sure you're always using those negative exponents. So folks, I will be looking for work on number 3 and number 4. This is just to save us a little bit of time in this video. All right, now moving on to number 5, this is where we kind of start taking it up a notch. We've got an exponential equation because we see that our variable is up in the exponent, but the problem here is that our bases are not isolated. Can I rewrite 1/7 and 14 is the same small base? Well, what about this 2 that's out in front of this base on the left side? So our first step is actually going to be dividing both sides of this equation by 2. So isolating that base. And how do I know that the 1/7 is the base and not the 2? Well, because the 1/7 has the exponent tied to it. So this leaves me with 1/7 raised to the x equals 7. So you could either solve this one in your head, or you can rewrite 1/7 as 7 to the negative 1 x equals 7. And we could say that that is to the first. So x is equal to negative 1. And again, folks, it never hurts to actually plug your answer back into the original equation to check yourself to make sure you get the same thing on both sides. So moving on to number 6. As I'm looking at this one, first I see that my variable is in the exponent, so this is an exponential equation. Are my bases isolated? No, they are not. So the first thing I'd want to do is subtract that 5 to move that over to the other side, which gives us 2 to the x equals 8. So then x is equal to 3. So again, those steps for solving exponentials are identifying it's an exponential with our variable up in the exponent, isolating our bases, and then try to get the same bases, or what we haven't encountered yet is logging or natural logging both sides. So let's see what happens when we look at number 7. First, how do I know that this is an exponential equation? We see that our variable is up in the exponent. Now to isolate this, again, think about what you would do if this was just like 5x minus 6 equals 9. You're essentially doing PEMDAS in reverse to isolate your variable. So we'd be adding 6. So 5 times 3 to the x equals 15. Now, sometimes students look at this and they go, wait, can I simplify the left? Like, can I actually multiply the 3 and the 5 together? The answer, folks, is no. And that's because this 3 has a variable exponent with it. So I can't combine these as like terms because they're not the same base and I wouldn't have anything to do with that power. So I can't simplify the left side, but what we can do is isolate it by dividing both sides by 5. So 3 to the x equals 3, and bam, x equals 1. Now, in your homework, I would like you to go ahead and draw a line after that first block of problems, because now we are ready to move into the log type of problems. So what I would like you to do is up at the top of your homework packet, we're going to write how we solve logarithmic equations. So when you have a single log or multiple logs, you're always going to start by isolating the logs. And that also means no coefficients, and we'll see that on some of these problems below. So just like we want to isolate our bases first for exponential form, we always want to isolate our log first for logarithmic ones. So if I have one log, we are simply going to put it in exponential form to solve. So exactly what we were doing a couple of days ago when we were trying to evaluate a single log. So solve one log, evaluate one log, put it in exponential form using big animal ears. Now, if we have more than one log, then you are going to either condense or cross off, depending on where those logs are located in the equation and if we have extra stuff. So we have a few more steps when we are solving logs, and the number of logs kind of indicates how we are going to be solving. Another extra piece of solving logarithmic equations is we're going to have to check for extraneous solutions. And remember, extraneous solutions are ones we can solve for algebraically, but they don't actually work. So how we verify if the answers we got are extraneous is that they would make the answer part of the log greater than 0. So let's go ahead and move down to number 8. And first, we identify this as a logarithmic equation because boom, it's got the word log there. So again, identifying an exponential, our variable is going to be up in the exponent. Identifying a logarithmic equation, you are going to have the word log written. So seems easy enough. Next, for solving log equations, we count how many logs that we have. Here, we've got one log, so we're going to put it in exponential form to solve. So we see the word log, we think of the elephant with his big animal ears. So our base is 2. Our exponent is x, and our answer is 1/16. Now, from here, now that I have it written in exponential form, this is now an exponential equation. So there is a difference between exponential form and exponential equations. This one happens to be both, so we'll see more of that as we work through this. But now that this is an exponential form, we want to try to solve it like we did the problems above, which is trying to get the same bases. So 2 to the x equals 1/16. I could rewrite 1/16 as 2 to the -4, or you might be able to just solve for x in your head. And we see that x is equal to -1/4. But before we put a box around this, we have to check to see if this is an extraneous solution because our original equation started off as a log. So if I look at the answer part of this log, that would be 1/16. Well, is 1/16 greater than 0? It sure is. So my variable or my solution doesn't actually affect the answer part of the log at all. So that truly is our solution. Mrs. Cairo, do we have to show this work up here? No, you don't have to. I'm just kind of doing this as part of the video so you know that that is how we know that this really is our solution and that it's not extraneous. Alrighty, so looking at number 9, how many logs do we have? We have a single log in this equation, and he is isolated. So to solve this log equation, we are going to put it in exponential form. So we think of the elephant holding that log in his trunk with his big animal ears. So our base is 1/3. Our exponent is x, and our answer is 27. Now, folks, I know that some of you guys can do a problem like this in your head, but anytime you're dealing with those fractions, I really do recommend that you rewrite these as the same base. So, again, it's a recommendation. I am going to be picky about work that I'm seeing on this assignment because the solving is especially important for calc. So, in order to get the same basis here, now that this is an exponential equation, how can I rewrite 1/3 as a ground level base? That would be 3 to the -1. How do we write 27 as a smaller base? That would be 3 to the third. So now that we have the same bases, we can cross those off. So negative 1x equals 3, and x equals negative 3. But before we put a box around it, because this is a log equation, we have to check for extraneous solutions. So we look at the answer part of the log, which is 27. And 27 is always greater than 0, so x equals negative 3 is really our solution. So, folks, let's go ahead and move on to number 10. So we have a log equation. It is isolated. There is one log, so we are going to put it in exponential form. So big animal, here's our base is 9. Our exponent is x, and our answer is 1. So I recommend pausing this video and see if you can figure out what value of x would make this statement true. So even though we can't solve it by getting the same bases, this is where we have to use our brain and say, the only way for me to get a base of 1 is to take a similar base to the power of 0. So remember, anything to the 0 power is 1, so that would be my solution. But before we put a box around it, because it's a log equation, remember with logs, that's where we have to check for those extraneous solutions. So we plug it into the answer part of our log, which is 1. Is 1 greater than 0? It sure is. So x equals 0 is our solution. And on that last one, 27 was greater than 0. So for these three problems, our variable has not actually affected our solution at all because it's been in the exponent position on the right side of the equation. So folks, in the next video, we'll take a look at a more complicated problem.